red light's on anyway. Okay, are we good to go? All right. So anyway, you can take the VSF of pure water plus this phytoplankton plus that phytoplankton plus mineral particles, and you get the total one, which is what you'll need to model the light field. Now, if I write beta as being scattering coefficient times the phase function, and then divide by the scattering coefficient, then to add together phase functions, you need to weight them by the fraction of the scattering that's due to each particular particle. So I'll often have a phase function for water, one for phytoplankton, one for mineral particles, etc. And I want to add those together and get the total phase function. I just have to weight each of those by the fraction of the total scattering that's due to water, the fraction due to phytoplankton, the fraction due to air bubbles, and so on. So then what components does it make sense to use when we want to model the total volume scattering function or the total phase function? Well, we're going to have water. We're always stuck with that. We probably want to have phytoplankton, maybe colored particulate organic matter, colored particular inorganic matter, aka mineral particles. Then maybe you also have air bubbles or oil droplets or whatever, so you add those in. Okay, so if we look first at pure water, there's a thing called Rayleigh scattering, which Rayleigh computed back in the 1800s, assuming that the scattering particles were very small spheres. And so he gets the green line here is scattering phase function. And then if you look at the phase function measured for pure water, you get the red curve. It's very similar to Rayleigh, but not quite. And why is the not quite? Why isn't it exactly like Rayleigh? Right, water molecules are not spherical, so that kind of messes things up a little bit. You get the red curve instead of the green one. And then if you look at the total scattering coefficient for pure water as a function of wavelength, well, the Rayleigh scattering curve is lambda to the minus fourth. The pure water curve is basically lambda to the minus about 4.32. It's not quite the same as Rayleigh, and once again, that's just an effect of the fact that water molecules aren't spherical. So you'll often see things like the phase function for pure water. They may use the value at 90 degrees, and then the angular value is basically a 1 plus a factor times cosine squared. And sometimes the later papers may have a slightly different value here. It might be like 0.87 or something, because they did another set of measurements with a better instrument and came up with something slightly different. Then you've got the scattering coefficient, and then if we multiply those things together, you'll often see that the total volume scattering function for water is maybe the value at a reference wavelength of 90 degrees, and then the wavelength relative to the reference to the minus 4.32, and then the angular part looking like this, and then you go to some table and look up the measured volume scattering function for water at 90 degrees and at some reference wavelength, and you can plug all those numbers in and get the total for any wavelength and any scattering angle. Okay, and all of that kind of stuff is built into Hydrolite, so you just click the button that says, pure water. Now, we saw, or you've seen in the labs, that absorption by pure water at some wavelengths depends significantly on the temperature, but it doesn't depend much on the salinity, and that's because the salts are non-absorbing. On the other hand, scattering is the opposite. For a given temperature, scattering depends significantly on the salinity, And so here's a temperature of 20 degrees C, salinities from 0, pure water, through 40 parts per thousand. Typical ocean water is maybe 35 or so. And there's about a 30% difference in the scattering coefficient at a given wavelength, depending on whether you're going from pure water, low scattering, to highly saline water at high scattering. On the other hand, the scattering coefficient almost doesn't depend on temperature. So it's kind of the opposite of absorption. Yeah, Melanie. Yeah, so for the absorption part, the salt particles are non-absorbing, so they don't mess with absorption much. The temperature, though, is causing the molecules to bounce around differently and all of this at certain wavelengths, and you get that. Here, when you put the ions in the water, the sodium and the chlorine ions, they attract the water molecules and they kind of change the structure of these little clusters of water molecules. So the like positive tails of the positive heads, if you wish, of the water molecules will kind of get attracted towards the negative chlorines, and the positive sodium ions will get stuck on the tails of the water molecules. And that's basically what you're doing, is kind of changing the shape and size of the scattering particle, and that then changes this. So to some small effect, yeah. But then no effect not much effect of temperature. It's all in the salinity part that matters. And once again, all these kinds of equations it's an enormously complicated bunch of math and physics. It's all built into Hydrolite. When you run Hydrolite, you click, for the pure water, I want a temperature of 20 degrees and a salinity of 15 parts per thousand, and it gives you the proper curve here. Okay, starting to look at some real world data now. So here's measurements of scattering by particles, and this includes phytoplankton and non-algal particles in case 1 and case 2 waters. Now, case 1 waters are waters where the chlorophyll-bearing particles, the phytoplankton, are what dominates the optical properties of the water. Case 2 is simply everything else. There may be extra CDOM, there may be mineral particles, there may be, resuspended sediments for mineral particles, whatever. So a lot of work has been done on case 1 waters because people try to parameterize everything there by the chlorophyll concentration. Down here, then just using chlorophyll doesn't make it. You need to also tell me how much CDOM is in the water that ran off from the land. You need to tell me what are the mineral particles in the water from resuspended sediments or river runoff or dust in the air, whatever. It gets to be a much more complicated problem. And the god of case 1 waters was Andre Morel, and he spent his whole career studying how to model case 1 waters. And I remember sometime at a meeting somebody said, well, Andre, when are you going to work on case 2 waters? And he said, well, I'm not. They're way too complicated. So anyway, that's now, like I say, getting much more attention. But bottom line, here's the particle scattering coefficient normalized by its average value over the wavelengths they measured. And you can see there's some wavelength dependence here. It's not really strong. And here's case 2 water, several different sets of data. There's a little bit of wavelength dependence. Remember, water was basically lambda to the minus 4. If we take these data here and plot them, well, here's a lambda to the minus 1 curve in purple. So these things, if you wanted to fit a curve through it, they might be like almost independent of wavelength, or maybe lambda to the minus half or something, but not even as strong as lambda to the minus 1. And there's a bunch of different waters represented here. So that's just kind of a general thing to remember, is that, these real world particles here, some wavelength dependence, but not really strong. Here's, historically, it was hard to measure scattering. This is pre-AC 9 days. So people would use me theory, and me theory says, well, if you have nice spherical particles and so forth, you should have this wavelength to the minus n, and if they were really small particles, n would be -4. That's Rayleigh scattering. If they're really big particles, n goes to 0, but typically n might be -1, a half, something like that. So people would model the scattering coefficient. They might have an instrument that measured it at one wavelength, typically 555 nanometers in the green. Then to get the scattering at other wavelengths, they would use a model like this, and they would just assume a value of n, something like -1. And, you know, that was the state of the art in 1980, let's say. Well, actually, Dr. Boss and company find that this kind of power law actually gives you a pretty good fit to beam attenuation. So you're better off to model the beam attenuation with this kind of power law, where now you've measured beam C at one wavelength, and then you get B from C minus A. So if you have non-algal particles, they tend to have kind of an exponential absorption curve, and this is a nicely behaved function of wavelength. So you take the beam C and you subtract the absorption, and once again you get a nice, very smooth function of wavelength. If it's a phytoplankton, the beam C may still fit this curve pretty well, but the absorption now has some bumps in it. So if I model for phytoplankton, here's IOPs of the phytoplankton, and beam C looks like this, and the absorption looks like this. Then when I subtract, the scattering is going to look something like that. But anyway, that's so not a nice smooth curve, but still, that's probably the best way if you have to do this kind of modeling because you didn't measure it. That's probably the best way to do it. And when you get to hydrolite, you can click, I need to model scattering. How can I do it? Well, you can pick an option to model beam C with this kind of function, or you can use some other function, and then you can put in your values of n and the reference wavelength and so on. So that's commonly done. Here's just absorption by some mineral particles, calcareous sand, yellow clay, red clay, brown earth, whatever that is. But these are measurements made by one of Morell's students way back when. Notice the measurements are from 400 to 700 or 750. I trust those numbers for that particular sample. Of course, there's a lot of different kinds of mineral particles, and in the literature you can find a lot of different measurements of mineral particle absorption and scattering. They all tend to look somewhat similar in that the absorption, for example, is higher in the blue than it is in the red. That's why when you mix the mineral particles in the water looks brown. It's because the blue is being absorbed and the red and the yellow are being reflected. And the same thing looks kind of true for the scattering coefficient. And notice here I've got mass-specific scattering coefficients. So what they did was they, as a function of wavelength here, they measured the total scattering, and it looked like this. And so that's units of per meter. And then they measured the concentration of the minerals, which is usually done in something like grams per cubic meter. That's just kind of the standard way people measure mineral particle concentrations, just like for chlorophyll, they measure milligrams of chlorophyll per cubic meter, or which is equal to liters of chlorophyll per milliliter, whatever it is. And so that's just the way people do it. So now you take the B, which is in 1 over meters, you normalize it by the concentration. So the concentration is in grams per cubic meter, and so this gives you the mass-specific scattering coefficient, which has units of meter squared per gram. That's what's plotted here. And so I've got the shape of the curve independent of the actual concentration. Now, I want to use this curve in hydrolite, and I say the concentration of the minerals is 2.2 grams per cubic meter. Hydrolite will, and I'm going to use red clay here, hydrolite will take that curve, it'll multiply this by your 2 grams per cubic meter, and that now gives you a B in units of 1/meter for your concentration of 2 grams per cubic meter. That's the way this modeling is usually done. And frankly, it wouldn't matter what units you use. You might want to have, I don't know, numbers of atoms per cubic, I don't know, let's say cubic centimeter. That's a stupid unit because the numbers would be like 10 to the 24th or something, but you could do it as long as you measure your concentration in number of atoms per cubic centimeter, so that this would now be, it would be centimeters squared per number of atoms, and then you'd multiply it out, and all that matters is at the end you get a scattering coefficient of per meter. So a lot of times people might measure something in some unit that's convenient for them, and then maybe if it's like CDOM concentration, it might be per mole or something, and then you just have to make sure you measure your concentrations per mole, and then this would be B star per mole times number of moles, and then you get units of 1/meter, and that's all that radiative transfer needs to have. The other thing to notice here is that the measurements were 400 to 700. When I had to build up the database for hydrolite so you could do a run from say 300 to 1,000, I just took these curves and extrapolated by eye. There's no physics at all there. And I have no idea whether for calcareous sand, maybe this goes like that, maybe it goes like that, maybe it comes up here and drops off, maybe it keeps going up. I have no idea because nobody's measured it. So somebody was asking me the other day, well, can I run hydrolite from like down to 200 nanometers? The answer is yes. Just tell me what all these databases look like at 200 nanometers. Well, nobody measures mineral particle absorption and whatever down to 200. The only thing that's been measured is pure water, basically. So it would take me 5 minutes to add the data to the database, and then you could run hydrolite down to 200 nanometers or out to 12,000, but I have no idea what I should use for chlorophyll absorption at 200 nanometers. And yeah.
Won't those measurements need to be done from PACE though, for hydrolite to be compliant with the PACE requirements?
I don't know what's being done there. Yeah, there is a fair amount of data you can find on some things down to 350, but almost never down to 300. And so anyway, the
don't know if the backscattering ratio is spectrally variant or not in your debates. There's a lot of still applying to
okay, here's more data. Here on the previous one, I'm looking at B star, the mass-specific total scattering coefficient, units of meter squared per gram. And I realized in the old days when I was in high school chemistry, grams were GM, and now it's just G. And I get all these emails from people in China saying, what the hell is a GM unit? Okay, I need to update my figures and just use G. Okay, here's now the backscatter fraction. So BB divided by B, backscatter coefficient by total. And it's often assumed that the backscatter fraction will be independent of wavelength. And in me theory, if once again you have spherical particles, etc., the scattering coefficient and the backscatter coefficient have the same wavelength dependence. And then their ratio is independent of wavelength. Now, is that true in the real world where you have non-spherical, non-homogeneous particles? It's actually pretty close. Here's a number of measurements of the backscatter fraction, BB over B, so non-dimensional, for a bunch of different stations, different water bodies. And you can see sometimes it's almost perfectly independent. Sometimes there's a little bit of wavelength dependence, but not a whole lot. And notice here, for your question, these backscatter fractions, these are mostly phytoplankton-dominated waters, and they're typically like 1 to 2%. Here's like, 1.5%, a little bit more, 1%, 1%. Those are typical backscatter fractions. Here's some more data here of backscatter fractions, and if you read the thing here, it says red circles are resuspension dominated. So that's mineral particles. Down to the blue, it says is, where does it say here? Yeah, blue diamonds, less energetic with higher chlorophyll. So the water with mineral particles has a higher backscatter fraction than the water that's dominated by phytoplankton. Why is that? What's the difference in phytoplankton and minerals? Yeah, the mineral particles are high index of refraction. It might be like 1.2, 1.22, something like that, relative to water. So that gives you more scattering. The phytoplankton index of refraction might be like 1.02, 1.04, somewhere in there, relative to water. If the phytoplankton index of refraction was the same as water, what would we see here? Yeah, there would be no scattering at all. So you get weaker scattering by low index of refraction particles than by high index, and also you get stronger scattering from these smaller, so you get a higher amount of backscattering by small particles than you do by big ones. So the mineral particles may also be a lot of really small mineral particles, and the phytoplankton may be big fat 5-10 micrometer size phytoplankton. So anyway, you see these differences, and here you see these are like 2% up to about 2.7% or something backscatter fraction, with a little bit but not a lot of wavelength dependence. Okay, so what is often done then to model the backscatter by particles is you take, here's our total scattering coefficient modeled as the beam attenuation fit by a power law minus the absorption by the particles, whatever they are, and then you say, okay, I need to convert the total scattering to the backscattering. Well, I do that with the backscattering fraction, and I'll use either measurements or models for this, and then I'll assume that the backscatter fraction is independent of wavelength, and I pick a value, 1%, 2%, whatever, and that would then give me the backscatter coefficient. So that's just something people commonly do because they weren't able to measure it. Okay, here's some examples of little models people have presented to give you the backscatter fraction, so this guy here, as a function of chlorophyll concentration. Well, notice here, for a given chlorophyll, there's a factor of 2 difference in these different people's models. Why is that? You can take chlorophyll, and you can do a pretty good job of predicting phytoplankton absorption. You take chlorophyll, you cannot do a good job of predicting phytoplankton scattering. How come? This is your PhD exam now. You're in front of the room, and I'm going to ask you this. Yeah, it's because chlorophyll is basically a measurement of how much stuff is in the cell. But whether you've got a small cell with chlorophyll of 5 or a big cell of chlorophyll 5 makes a big difference on the scattering. And of course, there's also the self-shading effects you get on absorption. But the effects are bigger on scattering because particle size and particle shape strongly affect scattering. So even though a bunch of particles have the same chlorophyll, they have different sizes and shapes, and that's going to give significantly different scattering. And I love this picture here. Okay, here's measured backscatter fraction at 555 nanometers versus chlorophyll. Look at this blob of points. And if you came to this and said, Curt, what's the function? What's the best fit curve here that will give me backscatter fraction versus chlorophyll? I would look at that and say, there's no relation at all there. For a given chlorophyll, let's say here's chlorophyll of 5, I can go from 0.5% up to 4.5%. I mean, there's just no real curve you can fit through a mess like that. But that doesn't keep people from fitting curves through it. And then they get these models where you predict the backscatter fraction given the chlorophyll. Maybe your water body has this value here and you're using this guy's model, you'll get a great result. But more than likely, you're going to use this model and your water's up here or it's down here and it's going to be total garbage. So just keep that in mind. Ken, are you stretching or asking?
Just a little, you read a paper or review a paper with some model and strung together one of these relationships, like 12 or 13 different relationships are all empirical, or the data looks like this, that they're scattering through. And then they say this is going to be the model, and then they use rescattering and do the rest of it. It's just like, come on, people.
Well, so one of the lessons is when you're publishing a paper that has a relationship, don't put the equation in the abstract. Because people scan abstracts and they don't read papers, so make them work to get to their numbers. So at least maybe they're like, oh, ooh, maybe there is no relationship. But if you put an equation in an abstract, guaranteed someone will use it incorrectly.
Yeah, Emmanuel.
Then there's another concept coming from atmospheric science. Chlorophyll is what's called an extensive particle. It's a particle that depends on the amount of material you have in the water. The backscattering ratio is an intensive parameter. It is not dependent on the amount of stuff you have in the water. It characterizes it in the water. And so often you'll find that if you did backscattering, you find a very nice, a good R square if you set all the motion because you have a good dynamic range in your properties. But always think about, is it intensive? Is it intensive, don't have much dynamic range? Look how small the dynamic range in backscattering is. It's about a factor of 6 encompassing most of the measurement capabilities. Chlorophyll instead is 5, 1,000. You have 3 orders of magnitude. So it's really hard to get the intensity. We want intensity, we want size. Size is intensive. We want shape, it's intensive. But then you don't have the dynamic range you can do with chlorophyll and everything else.
Yeah, Craig Boren has a great statement when he looks at stuff like this with curves fit through it. And he says, modelers just have to model. But he said there's an alternative to modeling. It's called measuring. So if you're in a water body, you need to measure, was your backscatter fraction this value or this value for the given chlorophyll? Then you can go about your business and get good results. But using one of these models, don't count on it. Okay, here's David McKee. He did some more measurements of backscattering by phytoplankton and non-algal particles. Now he's Scottish, so he went running around in the Irish Sea and the North Sea somewhere in this paper. And here he comes up with the backscatter fraction at 532 and it's anywhere from about 0.01 to about 0.06. So 1 to 6%, just depending on where he put his instrument in the water on which day. And then he sort of averaged all his measurements together. And yeah, there's some wavelength dependence here. And on average, this was somewhere around 5% down to 3%, depending on wavelength. And he's in waters which, once again, have, as far as I know, a lot of mineral particles in them. There's a lot of wave action, a lot of strong currents and stuff if you go around the coast of Scotland. And there's a reason why the Scottish are the best sea kayakers, because the water there is really rough and they really have to know their business. And because the water's really rough, you get a lot of resuspended sediments. Okay, so anyway, a few models for phase functions. Same story. Over the years, people couldn't measure phase functions because they didn't have instruments, so they cook up these models. And they're often models that were designed for, let's say, dust in the atmosphere or interstellar dust, and they may be good phase functions for atmospheric dust, but they're not good phase functions for phytoplankton. But people find the paper, oh, here's the phase function, I'll use it in the ocean. Well, you can see here the black curve is the Petzold average. Here's a curve here by a fellow named Haltran, obviously not even close to good. There's a couple others by other people that, sort of okay in here, but they're off by factors of 2 or something in the backward direction. And then there's the red curve labeled Fournier-Ferrand. It's the only one that does a pretty good job over the full range of scattering angles. So here's Petzold at small angles here. Fournier-Ferrand is very good. And then out at the backscatter directions, it's also very good, at least way better than these other models. So this fellow, Georges Fournier, Canadian fellow, is probably like the smartest person I've ever sat down and talked to. I mean, he's got like more IQ than the sum of the whole back row, including me. I mean, he's really a genius. But he works off in the defense sort of area, so you don't see him publishing a lot of papers in the literature, but he does amazing things with military optics, I guess you'd call it. Well, anyway, he sat down and he took me theory, which is enormously mathematical. Okay, so he said homogeneous spheres, real index refraction N. He picked a power law size distribution with the mu for the little exponent. And then he, some way with a pencil and paper, he integrated the me solution over all particle sizes from 0 to infinity. And one of the things that comes out of me calculations is the phase function. So he's got a phase function here that is what you would have for spheres over all sizes and for a given slope of the particle size distribution. Well, it's this horrible mess, but what goes into it, there's N, the index of refraction, there's a scattering angle, and then here's the slope of the size distribution. So you pick an index of refraction, you pick a slope for the particle size distribution, that determines nu and delta. Those things go in back up here, and pretty soon you get a phase function that's a function of scattering angle. And as far as I know, no one on earth can understand how he did this, but it's obviously correct because it does a really good job of fitting things like the Petzold data. So anyway, this is now used like standard thing in hydrolite. You say, I want a Fournier-Ferrand phase function with 2% backscatter, and it does the math for you. You can also, from his equations, you can get the backscatter fraction. And then here's a little plot of curves of constant backscatter fraction versus index of refraction and slope of the size distribution. So, for example, here's Petzold's average particle phase function has about 1.8% backscatter fraction. And so it's somewhere on this curve. And then I needed some way that I could put in a backscatter fraction and come up with an index of refraction and a Junge distribution slope, which I could then plug into the phase function formula. Well, I've got one number and I need to retrieve two, so that doesn't work. So I said, well, you know, Petzold's data in like San Diego Harbor, that's probably a mixture of phytoplankton and mineral particles, and phytoplankton are low index and the mineral particles are high, so maybe this average particle is something like 1.1, and I know the backscattering fraction, so I'll use this point here for the Petzold guy. And then phytoplankton have low index of refraction, so they're down here somewhere, so I'll pick a point here, or mineral particles are up here, high index of refraction, so I'll pick some point out here. So what I did, to show you what a good mathematician I am, I picked a point here and a point here from Petzold, and I was able to fit a straight line through the 2 points. That's pretty awesome, huh? So then I said, now, if you give me a backscatter fraction, let's say 3%, I'll come up to where the 3% curve crosses my straight line, and that'll give me an index of refraction of 1.2 and a slope of, 3.8. And I'll plug those into the formula to generate the phase function. And I put that in the paper, and I knew this is not going to get past the reviewers. They're going to say this is so hokey. There was not a single comment about it on the reviews of the paper. And so this is now like some way, it's like Petzold's data, it's a law of physics. Well, it's not. It's completely bogus even to the Petzold point. But it does allow me to pick a backscatter fraction and get a consistent set of index and slope parameters. And then I've done a bunch of runs now where you pick, say, here's a curve that's 0.5% backscatter fraction. If I pick this n and mu, or this one, and I generate the phase functions and use those in Hydrolite and compute remote sensing reflectances and irradiances and so forth, it turns out it really doesn't make much difference. As long as you have the right backscatter fraction, the details of what gave you that don't matter much. So that's what allows me to get away with this. Okay, so here's a whole family of Fournier-Ferrand phase functions that go from absurdly small backscatter fractions up to 40%, and then the green curve is pure water. And here's Petzold, 1.8%. So in Hydrolite, when you pick a 3% or 1%, whatever backscatter fraction, and you say, I didn't measure the phase function, so use Fournier-Ferrand, it will grab one of these curves here, and away you go. Okay, enough said. We showed you this before. Here's several different, sets of measurements, each with some particular scattering coefficient and backscatter fraction. Here I just picked out 3 or 4 of these curves. So here, there's a curve down at the bottom here that had 0.004 backscatter fraction. There's some curve up at the top here that went up to, say, about 0.03. And in each one of those, I used my little trick and generated a Fournier-Ferrand phase function, which is the red curve. And they do quite nicely, except right here in the backscatter, the last like 10 or 20 degrees. And I think the real world probably does come up, but I'm not sure about how good those data are. But basically, it's doing pretty good. And then the green curve is Petzold, which does fit the 1.83% backscatter fraction curve, but of course not the others. So that's kind of the state of the art for modeling things like that. Here's just some more data. This is in case 1 water, where Andre Morel measured the scattering coefficient at 550 versus chlorophyll, and there's kind of a factor of 5 variability as for a given chlorophyll. Here's where he added in some case 2 waters, and now you get, of course, even bigger variability. And then Morrell and Howard Gordon simply took this data and got the best fit curve through it and said that's going to be our model for the scattering coefficient as a function of chlorophyll, at least for case 1 water. And so here's their model. This equation right here for the scattering coefficient of particles says take 0.3 times the chlorophyll to the 0.62 and wavelength over lambda. Now, they only had one wavelength measured. Here's that curve right there, the blue one, for that 550 wavelength. And then they said, I don't know, let's just use a 1 over wavelength dependence, which is really too strong. But in those days, 1983 or whatever it was, that was the best they could do. And then there's also some equally old and simple models where there's an average of a bunch of phytoplankton chlorophyll-specific absorption curves. You can take those functions, plug into chlorophyll, get absorption by the particles, by the chlorophyll-bearing particles. You can take what people often did for CDOM was they would take the absorption by the chlorophyll-bearing particles, add in pure water, take maybe 20% of that, an exponential in wavelength, that gives them absorption by CDOM. And then there's the scattering. So when you run hydrolyte, there's a classic case 1 IOP model. There's the equations that are in it. You pick the chlorophyll and it plugs in these equations and away you go. There's been more recent work by Morrell and several others where, Nick Bricot, for example, where they now account, notice here, we're using the same shape of chlorophyll-specific absorption, no matter what kind of phytoplankton it is or what the concentration of chlorophyll is. Well, Bricot had a data set of 1,100 measurements of actual chlorophyll absorptions for all kinds of different phytoplankton. And then she's developed a model where, of course, here we see at the upper curve here, 0.03 milligrams per cubic meter of chlorophyll, down to the lower, flatter curve, 10 milligrams per chlorophyll. So, as you've learned, the shape of the chlorophyll-specific absorption depends on the chlorophyll concentration as you go from smaller particles to larger particles, and you get all the shading and pigment packaging and so forth. So she's actually got a model now where you take the chlorophyll and then she has these wavelength dependent coefficients, A and E, which are tabulated, and then you plug in the chlorophyll and the given wavelength and it will give you a better model. It will fit one of these curves. There's a different curve for each chlorophyll concentration. So you get maybe this curve or you get that curve or that curve. So you're doing a better job of modeling absorption. And then likewise, Morrell and company came up with better models for the scattering coefficient. They're still in terms of chlorophyll, but then they let this exponent, instead of being a -1 here, they let the exponent depend on the chlorophyll. And so that's probably a better function. And, you know, there hasn't been a lot of studies, but they do have a lot of data that went into this. And so when you run hydrolyte, you can pick the new case 1 IOP model, and it does all of this. And it actually also has a built-in phase function where Morrell has a large particle phase function. So notice low backscatter and a small particle phase function, so higher backscatter, and then the fraction of backscatter between these two is once again determined by the chlorophyll, so it will even pick a phase function for you. So that's Morrell's model, probably as good as there is out there right now. Okay, so the things not to forget is that as you've learned measuring absorption, you cannot just ignore scattering unless you're certain you don't have any particles in the water. So you always have to correct your AC9 for scattering. Well, the catch, of course, is that when you measure scattering, and you've got an instrument, so here the light comes in, it scatters, it's coming off, you're measuring the volume scattering function. Well, you're interested in the scattering, but of course light's also being absorbed along the way between where it's scattered and where you detect it. There's absorption along that. So to get a good scattering measurement, you need to correct for absorption. To get a good absorption measurement in your AC9, you need to correct for scattering. Anybody see a problem there? Like you need both of them, you need each one to correct the other one. So people have gotten fancier ways to iterate back and forth and so forth, and those are undoubtedly better ways to do things, but they're also much more complicated. So you always have to correct for absorption when you're measuring scattering. You always have to correct for scattering when you're measuring absorption. So you need to measure both of them simultaneously. And the other thing to remember is that IOPs are extremely variable. You know, chlorophyll goes by a factor of 1,000. IOPs can go not as wide a range, but you know, there is no phytoplankton absorption curve. There's a lot of them. There is no phytoplankton chlorophyll specific of scattering function. It's just so variable because of particle shape and so forth. And even for the same species of phytoplankton, you know, they have different nutrient conditions, they have different lighting history. They're in hot water, they're in cold water, so they get bigger, they get smaller, they're hungry, they're unhappy because they're too hot, they're unhappy because they're too cold, that affects their size and so forth, and then you get different scattering. So it makes it really hard to model IOPs. And these models, there are dozens of them out there, they're usually pretty good on average, but really they're just best fits through a data set. So on average, they're fine, but there can be a lot of variability about those averages. And 20-something years of experience shows that when hydrolyte gives the wrong answer, it's almost always because you put in bad IOPs that do not describe your water body. So if you want to do just like generic studies, you pick these models, you go, you get good average kind of results. If you want to model the Damariscotta River or Biscay Lake, you better go put instruments in the water and get the IOPs at that time and feed those into hydrolyte and forget the modeling. Okay, so the other things when you're dealing with one of these models, you got to think like, well, what data went into developing it? Was it from the Mediterranean? Was it from the South Pacific? Was it from Chesapeake Bay? Makes a big difference. And if you've got a global data set and you fit a curve through it, it's giving you a global average. It may be garbage for the Gulf of Maine, it may be garbage for the Yellow Sea, but on average it's pretty good. Regional models are not going to be good for elsewhere. You know, the phytoplankton in the North Atlantic are not the same kind of little thingies that are in the Southern Ocean, because the temperature and the nutrients are different and the lighting's different. If you have a data set that's for near surface waters where there's plenty of light, that may give you different relations than down deep where it's light limited. Open ocean data may not be able to be applied to, or models based on open ocean data maybe are not going to work in coastal waters because you've gone from little open ocean phytoplankton to big coastal diatoms, just different absorption and different scattering. And models based on me theory may or may not work for you because me theory assumes homogeneous spheres. And little bacteria are pretty good models they look pretty much like homogeneous spheres. A big chain diatom ain't going to work as a homogeneous sphere. And you also have to ask, where did they draw the line between case 1 and case 2 water? And if they developed a case 1 model, did they throw out the case 2 waters that had extra CDOM or extra minerals? And so you just have to think about these things. And there's no perfect IOP model, but there is a perfect building. And I always end my lectures with a pretty picture and a story of some kind, so at least you have something to look forward to so you don't walk out in the middle of the lecture. But anyway, I've spent a lot of time in China, kind of into Chinese history and culture and language and all of that. And if you go to Beijing, you go to a place called the Temple of Heaven, the Tiantan, and there's this building here which is called the Hall of Prayer for Good Harvest. And that's where the emperor had to go every year, go through about a month of rituals, purification, etc., and he would go in there and pray for a good harvest. And in European culture in the old days, kings had the divine right of kings. So you got to be the king of France because God picked you, and it doesn't matter how bad you screw it up, you still get to be the king of France. China, you had to have the mandate of heaven in order to stay emperor, and that meant no famines, no wars, no plagues. So you got to go pray for a good harvest. If you have a lot of bad harvests, you've lost the mandate of heaven. They get to throw you out. And there's been like a dozen times when things went bad and the peasants revolted and they threw out the emperor, and that's when you went from Yuan to Ming to Qing, etc., one dynasty after the next. So it's a different way of doing things. So anyway, it's an incredibly beautiful building. And you can tell in China, a building with a blue roof was for religious purposes. The emperor got to have a yellow roof. Civil administration buildings have a green tile roof, and ordinary peasants just get unglazed gray cement tile. So you can look at this building, you immediately know it was for religious purposes. And you look inside here, if you stand here and look upward, you just see this incredibly beautiful ornate decoration. And you notice here, there's square beams, and on top of that, the roof is round beams, resting on the square beams. Well, in Chinese cosmogony, it's cosmology, earth is square and heaven is round. So the emperor's geomancers determined that this is the point where heaven comes down and meets the earth. And so right there, where the round heaven and the square earth beams meet, is this point where heaven comes down and touches earth. And that's why they built the building there. Anyway, that's my story. Definitely got to go there if you're ever in Beijing. It's really it's a huge area. There's a lot of buildings, but this is the really good one. So that's my story. It's almost lunchtime, and obviously Emmanuel is not going to give an hour's talk before lunch, but I'll turn it over to questions, comments.
Figure out how to change the schedule.
And as I warned him, this is one of my longer talks, so the others will be 5 minutes shorter and have more equations. But I highly recommend pick some culture that's as different as possible from yours, which in my case would be China, and really dig into it. You know, learn something about the language, the history, the culture. How do they view different things? Like, how do you measure success? You know, what are the roles of men and women? You know, what's important in society? And what you learn is there's different ways to do the same thing. And I mean, with China, it sort of starts with chopsticks versus forks. And I'm perfectly at home with either one. And I don't think forks are better than chopsticks or vice versa. They're two different ways to solve the same problem. And you get that throughout the culture, you know, how you view where you fit into the society and all that. And there's nothing better or worse about one society versus the other. They're just different ways of doing things. And once you realize that, you've, I think, made a big step forward in learning how to, you know, live in the world. So anyway, that's my advice. So if you're from China, you know, pick Uganda and dig into Ugandan culture. And if you're from Uganda, pick Poland, you know, learn some Polish.
That is to just 2 hours noon here. We get back, we'll get back at 1:30. Let's get back here, and then